Hi, welcome to Teardown Tuesday. Yes, I'm excited. It's another oscilloscope. It's a new Rigol DS2000 series, and we haven't torn down a Rigol oscilloscope since the DS1052E, and that was years ago. Pretty excited to see what's inside this one. See if the build quality is any good. See if they've improved since the DS1052E. So you know what we say here on the EEVblog. Don't turn it on, take it apart. And for those of you who haven't seen the two scopes side by side, the new 2000 series has a much bigger screen. It's absolutely huge. And of course it's bigger, wider, it's about the same depth, but it's a fair bit heavier. So there's going to be lots of metal and shielding and stuff inside this puppy compared to the older 1000 series scope. So let's crack it open. And I do expect this thing to be pretty easy to take apart. There's no power button on the top, which when I took my original Rigol 1000 series apart, I actually broke off the knob. So we've got a few screws down the bottom here. That's about, I think, well, that's probably it under there. There we go. A couple under the handle, and they should pop right out. They're a little bit tricky, those top ones. Ta-da! And exactly what we expected. Full metal shielding. Check it out. It's got the fan on the side, and to get this off, it looks like we're probably going to have to take off this B&C nut here and a few screws on the top and the side there, but that should just lift off easily. And check out even the shielding they've put around the IEC mains input connector there. I like that. That's terrific. That is well done. They've got, of course, metal threaded inserts down in the case here, but let's take the rest of it apart and check out these two pin headers penetrating the metal shield here. Oh, it's got hack written all over them. If I look at the silk screen through there, that says SPI boot. Oh, that could be a hacker's delight, that one. And this one here is, look at the silk screen, it's got ground, VCC, reset, and what is BRGD, whatever that means. Go figure, but yeah, interesting. And here we go. I think I've got most of the screws out. Let's, hey, hello. Yeah, looks like it just lifts out. The fan is probably going to be attached over here, but that shouldn't be a drama. Fan and well, power. Here we go. Ta-da! We're in. Oh, beautiful. Look, it's all laid out for us. Wonderful. This is really looking quite nice. I'll just disconnect the main power rather tight. There we go. The fan, bang, and that's it. Oh, that's just beautiful. I love it when products are so easy to take apart like that. Wonderful. And at first glance, this board just looks beautifully laid out, and there's the input shielding can there, a couple of main heat sunk devices. We'll go into detail of all the parts, but it's just beautiful and accessible. I love that. And it looks like this board is going to pop out pretty easy too with these main screws here with these gold pads on them. And if we just undo that flat flex cable there, I think the rest of the board should just lift out. Probably we have to do, maybe undo the buttons on the front, the knobs on the front or something like that, but that's the main board. And here is the rest of the chassis, and check it out. They've got another beautifully shielded power supply here. They've I don't see any RFI bead on there at all, and it's probably not easy to see down in the IEC connector down in there, but they're nice, properly heat shrunk. Mains rated cabling coming down, beautiful little earth bonding point there with two separate wires, one coming directly from the IEC connector, the other one going off into the power supply. They're heat shrunk, they're properly crimped, there's a shake-proof washer on there by the looks of it. It's all really tight, beautiful, well designed. And look at that, they haven't skimped at the cable retention mechanism either. Beautiful. That's a double-sided adhesive tape one stuck down. It's all neat and tidy. It's just the correct length for the cable harness, just as long as it needs to be to get access to it and assemble and service it by pulling it back apart as well. Probably not designed by Rigol, probably subcontracted out to a power supply specialist company. Most companies do that. So I'd expect to see a quality and safe, well-designed power supply, probably not using prime spec, you know, Panasonic caps or something like that, but I certainly wouldn't expect one hung lows. Well, I may have been a little bit wrong on the third-party thing, because that's clearly got Rigol on it, and I can't see any other third-party markings on this power supply board. But wow, this is really good, folks. This is very well designed. Check out the Cellastic everywhere for starters. They've Cellasticed everything down. They're doing everything right. Let's have a look here. They've heat shrunk their inductors, their chokes on the input here. They've heat shrunk those. They're using proper mains rated caps, of course, as you'd expect. The inductors and transformers look first class quality. Hard to tell, but you know, it's just the vibe of it. Australians will know what I mean. And the capacitors here, all the output capacitors, they're EPCOS brand. There we go. They're not bad. They're not Capzon or anything horribly bad like that. They're all 105 degrees C rated. EPCOS. I like it. Lots of chokes on the output as well. So they're really doing the business there. Not sure what those output devices are. Not that fussed really, but they're, you know, they're all nicely insulated. They're doing all the right stuff. I see shake-proof washers on there, I believe. And that, folks, looks like a very nice power supply. You can see the split. I haven't taken the board out yet, but you can see the isolation, the high voltage isolation slot underneath those optocouplers there, feeding back to the primary from the isolated secondary side. So they're certainly doing the right stuff there. Doesn't seem to be a matching slot under there, although there could be. I'd have to take the board out to see that. But there's certainly spared no expense on the silicon stuff, just blobbing all this stuff down. There's your input bridge rectifier. By the looks of it, that's not heat sunk at all. Doesn't really need to be, but check this out. I like this. Bit of attention to detail. Look at that diode there. It's got a little ferrite bead on the cathode there of that diode. Go figure. They've determined, well, we need to slightly take the edge off that thing, so slightly take the edge off the waveform there. So we're going to whack in an RF bead onto that thing. Brilliant. I love it. Huge thumbs up. More isolation slots down here. There we go, to separate the earth from the active and neutral side of it. More slots down in there and up the top there. Oh, there we go. I don't think I can find a single thing wrong with that power supply, folks. I'd expect that one to last quite some time. I assume that the main 450 volt rectified DC cap there is also an EPCOS. It looks very similar. So I'd expect that one to last at a reasonable length of time. They've certainly done all the right engineering in that. Small attention to detail stuff. They've cable tied down that main cap. They've gone, well, the silicon is not good enough. We're going to do both. Really belt and braces kind of engineering. I really love it. And we've got our input surge protection, of course, input filtering stuff. So it's certainly designed to meet all of the international requirements for such switching power supplies. I'm sure they'd have no problem at all getting that type approved in any country. Now we'll take a look at the main board in more detail here, but beautifully laid out, nice and modular. Input can over here, your input triggering circuitry over here, some power supply stuff up here, a Rigol branded chip which we'll take a look at here, and we've got clip retained heat sinks here. But I'll just mention, somebody on the forum, their DS2000 series scope, actually these retaining clips weren't soldered on and they actually popped off, and his scope failed. It probably shorted out something else and it went ping, and apparently, so it's something to watch out for. It'll be interesting to see once we get this board out if mine is soldered correctly. But the soldering looks first class on this, by the way. Anyway, we've got processing up the top here, Blackfin processor we'll take a look at, more memory stuff. We've got all the power supply, nicely modular, just in the individual little modules. You can see the individual ground planes surrounding those. Beautiful. Now the only flux residue I can find on the board is around this presumably hand soldered front panel B and C connector here. You can see some of the residue left on there. Not a huge deal really. This looks like the soldering points over here, that would be for the front panel test point, test signal. But apart from that, the soldering really is first class on this thing, and I cannot fault it at all. And this is the external input trigger circuitry. It's got it even written down on the board there, external input. There's an input series resistor there, goes into a few large 1206 passives there, a bunch of SOT23 devices around there. That's a Texas Instrument branded chip, probably some sort of op amp or something, I'm not sure. And another device down there, little MLF package, not sure what's happening there. Another TI part, got quite a few TI parts there. P274 22K AV31, don't know it offhand. There's a voltage reference test point. There's a couple of more devices around there. It's all pretty bog standard stuff, and a 4051. Got to have a 4051. And check out the via stitching all the way around this external input circuitry. They've gone, oh man, I don't want anything to get in or out of this sucker. Let's just stitch the hell out of it. There's a couple of switching power supplies up in the top corner here, beautifully laid out. Look at the heavy via stitching on this stuff. Beautiful, nice, tight, compact layout. They've got them separately isolated in terms of the grounds. I'm not sure what voltages they are. They're probably, you know, core voltages for some of the main chips, like 1.2 volt core or something like that. Perhaps we've got a TDK buzzer on there, spared no expense. There's a 25 megahertz oscillator there. It's not the main one. There's a couple of them on this board, so that one's powering a chip. But look at this. Look at this puppy here. There's something on top of that chip. There's something on top of that. It's really rather weird. So that oscillator is clearly going into this little puppy here, and maybe that's sort of some sort of clock driver or something like that for the main Rigol device up here, which is a UZ0141. Who knows what that is? It could be a custom ASIC device. It could be just a you know, a rebadged off-the-shelf thing else. We don't really know, but clearly they've tried to disguise this chip down here for this main Rigol chip, which is driving presumably the clock in that thing. I can only presume by the location of this oscillator here next to this, and then the Rigol chip all the way over here. Can only presume that goes into here, and that goes off to the main Rigol ASIC. And check it out, it's almost as if like it's a bit of tape or something. You can see the laser markings on the chip underneath there. Now I'm going to try and scrape this off. It's only a tiny little thing. So it looks like it's on top. It's sort of almost like it's, you know, it's sort of baked on there or something weird. I've never seen anything like that before. Seems to be some sort of new method to sort of cover up the identity of what that chip is. Go figure. And they've got SOT 223, 1117 low dropout voltage regulators. There's quite a few of them scattered around this board. And as you can see, they've got a tiny little heatsink attached to them. Really nice little layout, nice via stitching. And if we have a look at the main Rigol device here, whatever it is, we can see all of the differential pair serpentine traces leading up to this main BGA device up here with the heatsink on it. And you can see how they're not only adding the serpentine parts into each pair to match, say, this pair here with the one next to it and match the length of the pair, but they're also adding the little single-sided wiggle in there to tweak and match the individual pair. It's each line in the individual pair. So that trace there with the wiggle in it is designed so that it exactly matches the length of its companion differential trace next to it. Classic, high-speed signal integrity layout. They've done it perfectly. And of course this board would be multi-layer, probably 6 or something like that. They might have even got away with a 4-layer on here, and that would be controlled impedance. And we've found ourselves the main sampling SD RAM. It is 512 megbit Hynix H5PS5162 GFA DDR2 SRAM, and that's SD RAM, and that's coupled into this main heatsunk device here, and there's a companion one over there as well, and they've also got another one here tied into, just the one by the way, not two, tied into this secondary device over here. Now I think we can figure out what this Rigol chip here is by deduction. Let's lift off the front end here, and we'll find that there's probably no ADCs under here. So, aha! And to get this can off, we're just going to have to bend up some little tabs we've got here, and that should allow us to, ta-da, pop the lid on it. There you go. Now we'll take a look at the front end later because it looks very similar to the DS1052E, but as you can see, there's no ADC in there. This is just a differential driver. So where are the ADCs, you ask? The data has to come out of the front end here, and it's got to go via differential pair, which will be on the inner layers in there. That's why you can't see any traces going from the input RF front end can over to here or anywhere else, because there's no surrounding. These aren't the ADCs here, right? I'm not sure what they are, but they're clearly not the ADCs. So clearly this custom device is the ADC. Now whether or not it's an off-the-shelf one and they've just rebadged it Rigol at the, you can do that with the manufacturer. You can get them to, if you order enough, say, I don't want your part number on it, I want my part number on it. But that has got to be, for all money, at least the analog, both analog to digital converters, multiple analog to digital converters, or something like that, controlled via this, this oscillator here will be like the master clock for it, and all that sort of stuff. And here are the outputs, all these differential pairs going from presumably ADC up to the main FP. Presumably this is an FPGA under here, which contains all the sampling, logic and all that sort of stuff, and it's got the 2 sample memory buffers next to it. Bingo, that's it. And then you've got the output from this flowing down over here into another FPGA or PLD, which we'll have a look at with some more memory next to it, and then eventually flows over into the main processor, DSP processor over here. So that's clearly what is happening there. And then if you're curious to know what this bunch of circuitry is here next to it, that's like probably another FPGA under there. We've got some memory next to it, another DDR2 SD RAM, but that's clearly the display processor. Look, it's just got a couple of lines going, maybe just a serial bus or something going from one side, going from the main acquisition ASIC well, ASIC, FPGA probably, over to this display processor here, because it's a dead giveaway of course, it's going down to the LCD display flat flex cable. So clearly that is the role of this device here. And then they've got some traces coming out of it by the looks of it. Once again, coupled into here, this FPGA sort of glues the data coming from the acquisition engine sort of into the display processor, and also takes commands from the DSP, which of course the DSP is not going to be doing a huge amount. It's just going to be doing like the user interface stuff and things like that. It's not, you know, busily updating the display. That's all offloaded to that display processor there. And if you remember the sampling memory here, 512 megbit each, divide that by 8, that's 64 megabytes, and there's 2 of them. This is a 2-channel scope, so that they'd probably be dedicating one of those per channel, of course. So this thing, well, in theory, has 64 megabytes of sample memory per channel. And on the display device here, we have 2 Cypress SRAMs, a CY731380C, and that's each one of those is an 18 megbit pipelined SRAM. So that's how they're going to get really super fast display updating on this thing. And for what I probably call like the glue FPGA here, they haven't gone for one of the big 2, Xilinx or Altera. They've gone for an Actel ProASIC 3, and it's got its own local oscillator there as well. And we've got some Spansion flash memory here, and also the JTAG header down here. So this thing, pretty much a hacker's delight really. And then linking these two, we've got some LVDS bus drivers there, and then we've got an ISSI 256 megbit SD RAM. That's a IS42S16160D, which is clearly the main memory for, ta-da, the analog devices Blackfin processor. And that's an ADSP BF526. I'm not sure if that's the same one used in the Rigol DS1052E. I forget, but there you go. That's the main processor. This is probably a flat flex cable going over to the keyboard, or the keypad, front panel keypad. And there's presumably the USB host interface. Haven't looked that one up, but that looks like a Cypress USB host. And we've got our Ethernet interface as well, all tied into the Blackfin processor there, with its own dedicated SD RAM memory. And then we've got the flash as well. That's all the program flash. And then of course we go over into this glue FPGA or whatever it is, and back again into our display processor. And there's that tantalizing SPI boot header. And then this mysterious one over here, ground, VCC, reset, and BKGD. And this circuitry here is coupled around the front panel USB connector here. So they've got their own local regulator here, and these devices, these two chips here, would be associated with power, providing power, current limited 500 milliamp power to the front panel USB port. And here's the date code: DS2000 mainboard version 1.00, 19th of March 2012. And you'll note that the real-time clock crystal there, a little bit bodgily soldered down, but at least it is soldered down, held in place. Bit of solder residue, flux residue left on there, but yeah, not a big deal. So although I can see the thermal grease under there, I am actually going to try and take this sucker off and see if we can get access to see what that device is under there. My guess is an FPGA of some sort. Should be able to clear that off and see what we've got under there. This is the display processor. And surprise, surprise, it's a Xilinx Spartan 6. Pretty new technology there, XC6SLS25. And that contrasts with the Actel FPGA we found elsewhere. So what's the bet? That this one up under here is also a Spartan 6. So unless they had drastically different system requirements for these two devices, then they probably would have made sense to consolidate and, you know, into the one part and choose a Spartan 6 under here as well. But it could be something else. We'll see. There you go. I was bang on. Spartan 6 as well. XC6S LX25. So, hey, they got those at a discount. And it's most likely that both of these will be sharing that same JTAG interface up there, because I can't see another JTAG interface for this one over here. So all up there, we've got 3 JTAG interfaces, one up here for these two Spartan 6 FPGAs, one over here for the Actel the smaller Actel FPGA, and one over here for the Analog Devices Blackfin DSP processor. And here's the front end analog input, and it is quite reminiscent of the DS1052E, although there seems to be a bit less in here, I think, or maybe it's just spread out a bit more. Now both channel 1 and channel 2 look to be absolutely identical, so we're only looking at channel 2 here. As you can see, we've got a couple of relays in here. We've got a couple of trimmer caps in here for this switchable attenuator part of it for the higher end voltages. We've probably got our this, I haven't looked at the part number yet, but that probably will be a programmable gain amplifier driving the ADC. That'll be a differential output programmable gain amp. There'll be a JFET and a couple of transistors in there to drive that thing. High speed op amp over here, and I think its operation is going to be pretty very similar to the DS1052E. Of course, these scopes have a upper bandwidth limit of 200 megahertz as opposed to 100 megahertz in the DS1052E. So it's basically just more of the same. They've just upped it to 200 megahertz. They've chosen specific parts and, you know, tweaked it to be able to do that. And I'm having a hard time reading that presumably programmable gain amp chip there and the one next to it. So I'm going to have to get out the digital magnifier. And woohoo, what do you know? I'm not sure if that's easy to read there, but that is Rigol. They've got a custom Rigol branded chip there. But once again, it may not be a custom device. I probably doubt it. They've probably just, maybe to prevent reverse engineering or something like that, they've just asked the manufacturer to relabel it and rebrand it as Rigol for them. But you know, I don't know. It could be custom, but I doubt it. And if we have a look through our Mantis scope here, there's the culprit, Rigol VM13AB. Whatever on earth that is. But yeah, my guess is it's a programmable gain amp differential output. And I'm not sure if you're going to be able to see that, but the other device inside this front end has got like that magic tape on it or something that we saw on the other chip on the main board earlier. So they're clearly trying to you know, stop reverse engineering or hacking of this thing by masking a couple of the chips in there. Bastards. So is it hackable like the DS1052E to get the increased bandwidth? I don't know. Your guess is as good as mine. Is there a varactor in there like the other one and they just switch it in digitally controlled under the software to limit that bandwidth in the amplifier? Perhaps it could very well be in there, but I'll leave that up to somebody else can hack. They've probably fixed the software thing, so I'd be very surprised if you could just do it easily through software, as easy as it was last time anyway, because they've shown that they've fix those things with the firmware upgrade. So, you know, but it's the easiest way to bandwidth limit these things is in the analog front end. They wouldn't be doing it in software. I think there's still got to be a line coming in here with some sort of you know, hardware filtering of that analog bandwidth. Now this section here is interesting, right next to the channel 1 input here, and there's 4 devices here. There's a presumably a local regulator powering it. There's some other little SOT23 device down here and another device up here. And if we zoom in on it, then I'm not quite sure what that device is. It's got 21AD3878 on it. There's a couple of voltage points next to it. One is 5 volts, so presumably that's not 0.5 volts, I think that's a little plus 5 volts and a plus 6.3 volts over here. Geez, what is it, a valve heater or something like that for an old valve? 6.3 volts, wasn't it, for the heater for the old valves? I could be wrong. I'm sure I'll be corrected by one of the old greybeards, but there are 4 of these like that. Identical layout, there we go, local low dropout reg, 1117 again. And then we've got another TI device, a HA595, and there it is, channel 1 sec, channel 1 FERT, channel 2 FERT, channel 2 sec. And that's pretty much all she wrote on the main board there. I mean, you know, there's a couple of stuff here for the backlight inverter, another a couple of core voltage, switch-in voltage regulators around there for core voltages for various FPGAs and things, but yeah, that's about it. I'd say we let's try and take this board out, flip it out, and see what's on the, you know, the underside. There's going to be some bypass caps on there clearly, because there's no bypass caps anywhere around any of these devices at all. And of course these FPGAs here, fairly dense Spartan 6s, they need bypassing on the bottom and everything else. So there'll be a bunch of passives on the bottom, and that's probably it. But there'll be another board on there for the front panel as well. So here we go. It's not easy to get this board out. You've got to take out the metal frame first, take all the knobs off the front, of course, and these are all metal threaded inserts on here. Beautiful, molded. There's the buttons, no problems whatsoever. And we'll have to take, no doubt, the B and C off here, but here's the front. Here we go. This is rather interesting. And check this out. Look what it says. Secretary Bird, SM key 02. Secretary Bird. What is that, the code name for this thing? Curiously, I think it has something to do with that symbol there, which is probably the secretary. Secretary? Australians will get that joke. Secretary Bird, perhaps. Is it the name of an actual bird, or is it? I don't know. And what do you know? There is such a thing as the secretary bird. It's from Africa. Go figure. There's not a huge amount on this board, just the rotor encoders. These are all pushable, of course, and we have the nice spring-loaded zoom knob here. Rather like that. It's really sexy. And there you go. There's not a huge amount doing on the back here. The 2 channels, they've actually removed the bottom ground plane out of that for signal integrity performance reasons, but apart from that, yeah, we've just got some basic passives, and there's some resistor terminators on there. There's the bottom of the BGA down in there. If you want to zoom in on that, you can see the classic bypass capacitor layout for an FPGA. Sort of, done that dozens and dozens of times, that star arrangement like that. That's just the way they generally fit in terms of the power pins under the BGA. There's some resistor terminators, nothing terribly exciting. The main processor, I think that's the main, no, that's the other FPGA up the top there. They're the 2 memories, DDR termination resistors, and that is about all she wrote on this board. There's the soft power button down there. Of course, this thing is operational all the time, and it gives that heartbeat type LED on the front power button, and you can see some residue on there as well. All these hand soldered connectors certainly have a bunch of residue left. They haven't used no clean flux on there, but not a huge deal really. What's that device in there? And it's another TI chip. Not sure what that one is or what it's doing, but there you go. There's the bottom of the that custom Rigol chip on the front end there. and it's identical between channel 1 and channel 2. And here's the back of the keypad board. My guess would have been a little micro or something like that, but it's a lattice Mark IO PLD. And what they've done is completely gunked up this flat flex cable. I don't know if there's a connector under there or not, whether or not it's maybe soldered directly on or something like that, but that runs under the LCD over to the other board over here, which then goes off to the main board down the bottom there. And the other thing to note too is there's a cutout in the metal panel here, and there's also a molding in the front panel for some sort of small connector interface. I don't know, a potential digital section? I don't know, your guess is as good as mine. Check out this soldered tab going over the top from the keyboard board here to the main chassis. They've decided that they've got to ground that for some EMI, reason. And it's time to reassemble this thing. It was a pain in the butt getting the buttons through the front panel. By the way, if anyone's looking at taking these apart, getting it back together is not necessarily easy. Beauty. So there you have it. There's the new Rigol DS2000 series. This is the DS2200, but they're all the same. Wrong knob. Oops. Interestingly, the silk screen on that front panel is all the way under the knob there. There you go. Go figure. And that is a beautifully engineered scope. I really like it. I mean, this is an $700-800 class scope, of course, for the entry level one. I mean, the analog bandwidth you're just paying for, software options, basically. Oops. Yeah, wrong knob. Oh, there we go. There's our scale knob, which should be bigger. Bit disappointed that the horizontal's the same. That's a trend with all scopes these days. I long for the day when they have a nice big horizontal. You think this would be the horizontal. It's not, it's the zoom. Oh man, very Tektronix-like there. But there you go. That is the new Rigol DS2000 series scope, and that is an absolute winner. It really is. That is beautifully engineered for, the sub $1,000 price category. I think it's awesome. I really couldn't fault the engineering in this thing at all, and I think it'll be a pretty darn reliable scope and probably pretty hackable as well, I would suspect, and I'm sure there'll be no shortage of people working on that just for fun, play a game of Pong on it. Go figure. Anyway, if you want to discuss it, jump on over to the EEVblog forum, and if you like Teardown Tuesday, please give it a big thumbs up. Catch you next time.